In chapter 1, I briefly talked about the scalar and vector quantities, but in this chapter, I'm going to talk about vectors in general in physics because they're the very big part of this course. So we need to know how to break a vector into its component and how to add them and subtract them. Starting with scalar, we know that a scalar is a number with units. This can be positive, negative, or zero. But sometimes this scalar is not enough to describe a physical quantity, and this happens in many cases that we need a direction. For example, suppose that you're walking in an unfamiliar city and you want directions to the library or to the airport. Now, if you just ask, do you know where the airport is? And the person replies, yes, and then it's in 3 meters, then that is not very helpful. But instead, if it says, yes, it is a mile from here, but it is in, for example, like 2 blocks to the northwest of here, then this is most helpful. So what I'm trying to say here is that with both distance and a direction, then you can exactly know the location of the library or the airport. So with this, we define the vector as a mathematical quantity with both magnitude and direction. When we indicate a vector on a diagram or a sketch, we draw an arrow. Okay, so if I want to use a vector, for example, if you are here and then this is the east and this is the north and this is the west and this is the south, so maybe this should be a bit shorter. Okay, and then let's say that this is the ugliest circle ever, but let's say that this radius is 0.5 miles, right? Okay, so if I just tell you that the library is 0.5 miles away, then the library can be here or here or here or here or here, anywhere, right? But if you want to specify where the library is, then you can just show it by this vector, which is the distance vector or radius vector, and we call it r. Now, to indicate a vector with a written symbol, we use boldface for the vector itself with a small arrow above it to remind us that it is the vector nature. So this quantity has the vector nature. Okay, so I use it in the equation, for example, r and with this above it. Or you can just put r and an arrow above it. So these are like both the same. So this means that this is vector r. It's not a scalar anymore. So if I just write r is half miles, this means that this half mile is the magnitude of the vector. But if I put r equals to half miles northeast, then this is the vector r. Another important topic here is to define the components of a vector, of the vector. So to find the components of a vector, the first thing is to set up a coordinate system. So in one dimension, it's either in x direction or y direction. When it comes to 2 dimensions, then we choose an origin O and a positive direction for both x and the y axis. For example, I can just use a coordinate system like this with the origin to be 0 or what we call O, and then this is the X, and this is the Y coordinate system. Now, if we are talking about the 3 dimensions, then we need to have another axis. Let's call it Z-axis, okay? So this is for later on. I'm just gonna like show you here quickly so that you know what is going to happen in future. But for now, we're just sticking to the 3 dimension, to the 2 dimensions. So this is X, Y, and Z. So this is like when you look at the corner of your room and you see like the corner of the room, it has two axes, X and Y, on the floor, and there is the Z axis that shows the height of the wall, right? So this is just like X, Y, and Z that I showed it here. Okay, so for now, let's forget about it and stick to the 2 dimension. Okay, now in this coordinate system that has an X and Y axis, so this is a positive X direction, this is a positive Y direction, a vector is defined by its magnitude, which is indicated by the length of the arrow representing the vector and its direction. Okay, so if I want just to draw a vector here, I can draw vector R. So if this length, the length of the vector is 1 point, for example, 10 meters, and then the direction, I can use theta to show what is the angle that this vector has with x-axis. So let's say this is 25 degree. Okay, now equivalently, what we can do is that we can define this vector r by saying that it extends a distance rx in the x direction and a distance ry in the y direction. Let's see what happens here. So I'm going to draw the coordinate system again. So this is x, this is y, this is my vector r. So what happens here is that this vector has components. So it has this component here, which is r sub x, and it has this component here, which is along the y-axis, and this is called r sub y. Okay, now in this angle is theta. We can find the value of our x and our y by using the standard relationships. Okay, so these is something that you should have studied in the Calc 1. So what we know is that the magnitude of Rx, which is the magnitude of my vector in x direction, is the magnitude of R times cosine theta, and then the magnitude of R along y-axis is equal to R sine theta. Okay, so if R is 1.1 meters and theta is 25, let's find them. So Rx is going to be 1.1 meters cosine 25 degree. So it's going to be 0.997 meters. And then Ry is going to be 1.1 meters sine 25 degree equals to 0.465 meters. So I know that this is 0.997 meters, and then Ry is 0.465 meters. So these are the components of the R vector. So we can show the vector in 2 ways. So in the first way, that is that you just show the magnitude of the vector, for example, r equals to 1.1 meters, with the angle that it makes with the x direction. And this is the standard way. We always calculate the angle that it makes with the positive x direction. Or in the method 2, you can show a vector by its component, meaning in 2 dimensions, by its x and y component. Now let's do it opposite. What if we have the components of a vector and we want to convert it to magnitude and directions? Okay, so sometimes this is what happens here. Okay, for that we need to look at another vector. Let's say this is my vector A, and let's say that this is my coordinate system x and y. So you can just show this like small thing here to show that how you consider or set up the coordinate system. And then I know that this vector has a component ax and ay, and the angle that it makes with the positive x direction is theta. All right, so according to the equations that I know, sine theta equals to opposite divided by hypotenuse, and then cosine theta equals to adjacent divided by hypotenuse. Okay, so if I rearrange this, this is what we got in the what did I do? Sorry, this is the adjacent, right? So I'm gonna rearrange for x and y component, and I'm going to get exactly what we derived in the previous page. So this is a cosine theta and a sine theta. All right, so another thing that I know is that the hypotenuse, the magnitude of hypotenuse is always square root of the x component or the adjacent square plus the y component or opposite squared. So these are the equations that you need to know by heart, because this is what we're going to use in this course, like from now on. Another thing is that, okay, now if I have the component x and y, this is how I'm going to get the magnitude of the vector. But what if I want the direction of the vector? Then I'm going to use this equation, tangent theta equals to the opposite divided by the adjacent. Or I can say theta is tangent inverse of ay to ax. Okay, so if you have the x component and y component, you can get the magnitude and the direction of the vector. For example, in the previous page, on the previous page, when you had Rx and Ry, so you can just simply find R to be square root of Rx squared plus Ry squared. So it's going to be square root of 0.997 meters squared plus 0.465 meters squared. So this is going to give me 1.1 meters, and you can actually calculate it. And then you can get theta from tangent inverse of Ry, which is 0.465 meters divided by this is Rx, 997 meters, and then you calculate it and you get 25 degree. So you can either use tangent or you can use cosine theta or sine theta, and any of these that you are more comfortable with. Another importance that knowing the components of a vector have for us is that they are useful in adding and subtracting vectors. Okay, so let's begin by defining vector addition graphically, and then we'll show how the same addition can be performed more accurately with the components. Okay, if you have a vector A and vector B, and just imagine that they show just the displacement to you, okay? So we want to find vector C, which is the addition of vector A and B. So to add the vectors A and B, place the tail of B at the head of A. Okay, so for example, if you have even A and B like this, then what you're going to do is that you're going to place the tail of B at the head of A. Then the sum is the vector extending from the tail of A to the head of B. The tail of A to the head of B. Here you go. Another example. If you have A, B, and then C. So we are going to start with A. Oops, I just say A and write B. And then we are going to place the tail of B at the head of A, but exactly with the same direction. So I'm trying my best. Let's say that this is B. And then I'm going to place the tail of C at the head of B. So one by one, okay? So let's say so with the same magnitude and same direction. Now the summation is the vector that extends from the tail of the first one, which is A, to the head of the last one, which is C. So this is vector D. So let's say D is going to be A plus B plus C. Another topic that you can see on page 867 on figure 312 is that for you to see how A plus B, which is C, is equal to B plus A. So in summation, the orders do not matter when it comes to vectors, because here A plus B gives you this vector, and then B plus A exactly gives you the same vector. Now, I do not have the tools to perfectly graph this for you, but if you go to page 67 and take a look at the figure 312, then you can see exactly how it works. All right, now this was all about adding graphically, but then we can add the vectors using their components. So this is way much easier and makes our problems very, very simple. If you want to add the vectors using their components, what happens is that you simply add the component together. For example, I'm going to just draw this figure for you so you can see here. So I have vector A, right? And then the components are here A x and A y. And then I have vector B that has the component of bx and by. All right, the resultant vector, I'm going to show it by dash, is vector C with the component cx and cy. So as you can see, even on the graph, cx is ax plus bx, and then cy is ay plus by. So what you do is that first of all, So step one, you break A to AX and AY. So meaning you find the components of A and then you find the component of B Bx and By, and then add x's together, which gives you, seriously, cx, and add the y's together, which gives you the component x and y of the resultant vector. And at the end, to find c, we are going to use this equation, square root of cx squared plus cy squared. Okay, how do we subtract vectors now? Suppose, for example, that we would like to find out that what is vector D, which is A minus B. So a trick that I'm going to use here is that I simply write D to be A plus negative B. All right, so D is the sum of A and negative B. Now, the negative of a vector has a very simple graphical interpretation. The negative of a vector is represented by an arrow of the same length as the original vector, but pointing in the opposite direction. For example, if you have x and y, and this is b, then negative b is going to be the same length, but in opposite direction. Okay, so if I have a and this is b, and if I want to find a minus b, so what I have to do is that I'm going to draw the negative b here and then simply add a to the negative b. So this is my vector d. D is a minus b. So same thing happens when I want to use the components to do that. So again, I'm going to just find the x components, and then dx is equal to ax minus bx here now. Then the dy is ay minus by. And then once I have the components, then I can say d is the square root of dx squared plus dy squared.